Today I want to tell you how you can treat random variables as vectors. That way we can use the tools of linear algebra and vector spaces to discover new ways of looking at our random variables. As always, let's start with the story. The chest of the Mad King Tryphon had been lost for centuries and was known to contain thousands of gold and silver pieces. In fact, the explorer modeled the treasure as being equally likely to contain 00, 01, 02, 12, or 11, where, for instance, 1, 2 would mean that there were 1,000 gold pieces and 2,000 silver pieces. What is the covariance between the number of gold pieces and the number of silver pieces? To answer this and other questions, we're going to need the notion of a vector space. Now, a vector space is built up from two types of objects: vectors, which can be added together to get new vectors, and scalars, which can stretch out vectors to get new vectors. Displacement vectors are typically the first type of vector encountered. In such a vector, the tail of the vector represents the starting location for an object, and the head of the vector shows where the object has been moved to. While this is a common type of vector, it is far from the only kind. In probability, real-valued random variables can be considered vectors, and then real numbers can be considered scalars. If x and y are random variables, then x plus y is also a random variable. So if these are thought of as vectors, adding them together yields another vector. Similarly, multiplying by a scalar gives something like 4x or negative 2y, which again are random variables. But that is not the only way to set up vectors. Suppose that x is an integrable random variable and so has a finite mean. Then the centered version of the random variable can be defined. For an integrable random variable x, x sub c, which is x minus the mean of x, is the centered version of x. Now, the centered version of an integrable random variable always has mean 0. The value mean of x is a constant, and so the expected value of x minus its mean is the mean of x minus the mean of x, or just 0. Now, if x and y both have mean 0, then for any real numbers a and b, the mean of a times x plus b times y will also equal 0. And this just follows from the linearity of expectations property of the mean. Now, why is that so important? Because in order to qualify as vectors, linear combinations of these vectors must also be vectors. A vector space is a set of vectors v together with a set of scalars s and two operations with the following properties. First, there's vector addition. The sum of two vectors is also a vector. This addition is associative and commutative. Also, there's a zero vector, such that when I add 0 to a vector, I get the vector back. And there exist inverse vectors, so that v plus the inverse of v returns the 0 vector. Next, there's scalar multiplication. When I scale a vector, I get another vector. This multiplication has an identity element 1, so that if a vector is scaled by 1, it just returns the original vector. Also, for every pair of scalars in vector v, if I take a times b times v, that's the same as a times vb. It's also distributive in two ways. Scalar multiplication distributes over vector addition, and scalar addition distributes over scalar vector multiplication. Now, it is straightforward, if a bit tedious, to verify that these rules are obeyed by our centered random variables. So if v is the set of random variables with mean 0 and s are real numbers, then v together with s does form a vector space. Now, some vector spaces have what is called an inner product that applies to pairs of vectors. For displacement vectors, the value of the inner product tells us about the angle between the two vectors. For centered random variables, the inner product tells us how the value of one variable affects the average value of the other variable. When the inner product is high, a high value of one centered variable leads to a high value for the other. When the inner product is negative, then a high value of one centered variable leads to a lower value for the other. In general, an inner product is defined as follows. For a given vector space V and S, a real valued inner product is a function that maps pairs of vectors to a real number with 4 properties. We use angle brackets around x and y for the inner product of x and y. Now, the 4 properties obeyed by an inner product are similar to the properties that general multiplication has. First off, it's distributive. The inner product of x plus y with z is the product of x with z plus the inner product of y and z. Scalars can be brought out of inner products. So the inner product of alpha x and y is alpha times the inner product of x and y. It's symmetric. So the product of x and y is the inner product of y and x. And finally, the inner product of a vector x with itself will always be greater than or equal to 0, where equality holds if and only if the vector is the 0 vector. Now for displacement vectors, the usual inner product that you learn about in linear algebra is called the dot product. For integrable random variables, the inner product is called the covariance. So here it is. Given integrable random variables x and y, if x times y is also an integrable random variable, then define the covariance between x and y as COV of x comma y, and it's the mean of the centered version of x times the centered version of y. In mathematics, the term norm refers to the measure of the size of a vector. To be a valid size, a norm needs to have 3 properties. First, if you scale the vector by c, the norm of the vector should scale like absolute value of c. Second, the triangle inequality holds. The norm of the sum of 2 vectors is at most the sum of the norms of the vectors. Finally, a norm evaluates to 0 if and only if the vector is the 0 vector. Formally, we write this definition as follows. A norm of a vector space takes as input a vector and returns a non-negative real number. Write the norm of v as v with 2 vertical bars on either side. All norms obey the following rules. Number 1, for any scalar c that's a real number and vector v, the norm of cv is the absolute value of c times the norm of v. Second, for any vectors v and w, the norm of v plus w is less than or equal to the norm of v plus the norm of w. And third, for any vector v, the norm of v is greater than or equal to 0, and only equals 0 if v is the 0 vector. Now for vector spaces with an inner product, one easy way to build a norm is to take the square root of the inner product of a vector with itself. So we call the norm of v, that's the square root of the inner product of v with v, an inner product norm. When the dot product is used with displacement vectors, this gives the Euclidean norm, which is commonly considered the length of the vector. If covariance is used as the inner product, the covariance of a random variable with itself is called the variance. The square root of the variance then gives the norm called the standard deviation. Definition: the variance of an integrable random variable x is the mean of the centered version of the random variable times itself. The standard deviation of a random variable x is the square root of the variance. Now, the definitions of covariance and standard deviation are actually not the usual way for actually calculating those values. Instead, the following formulas are often used. For integrable x and y, the covariance between x and y will be the expected value of the product of the random variables minus the product of the expectation of the random variables, which means that the variance of x is the mean of x squared minus the mean of x quantity squared. To see why this is true, consider the covariance of x with y. That's the mean of x minus its mean times the quantity y minus its mean. If we use FOIL to multiply that out, we get four terms. X times y, minus y times the mean of x, minus x times the mean of y, plus the expectation of x times the expectation of y. When we take the expectation of this, we can use linearity of expectations to say that this is the mean of x times y, minus the mean of x times the mean of y, minus the mean of x times the mean of y, plus the mean of x times the mean of y. And these last three terms combine to just give us a minus mean of x times mean of y. Applying the covariance result to the variance tells us that the variance of x, being the covariance of x with itself, is the mean of x squared minus the mean of x times the mean of x. So now we're ready to solve our story from earlier. Now for each of the possible x, y values, 0, 0, 0, 1, 0, 2, 1, 2, or 1, 1, each of those is equally likely, and so each has density 1/5. So if I want to find the mean of something like x times y, I'm going to take those probabilities, 1/5, 1/5, 1/5, 1/5, 1/5, and I multiply x times y. So for instance, 0, 0 becomes 0 times 0. The point 0, 1 becomes 0 times 1. The point 1, 1 becomes 1 times 1. Overall, the expected value of the product of x and y will be 3/5. I can do the same thing with just replacing x times y with x to get 2/5. And when I replace it with y, the possible values are 0, 1, 2, 2, and 1. I end up with 6/5. That allows me to put it together and say that the covariance is 3/5 minus 2/5 times 6/5, or 15 minus 12 over 25, or 3/25, which is 0.12. Now remember that each one of those numbers represented 1,000 gold or silver coins. So if x is the number of thousands of gold pieces and y is the number of thousands of silver pieces, then by the rules of covariance, if I multiply each of those numbers by 1,000, I can factor out a 10 to the 6th power. And so I'm left with 120,000 as my final answer. I said that covariance was an inner product. Let's just check and make sure that it satisfies each of the properties, one property at a time. The first property that we're going to check is that it is distributive. So if I look at the covariance of x plus y with w, that's the same as the covariance of x with w plus the covariance of y with w. All we have to do is write out the definition. We've got the expected value of the quantity x plus y times w minus the mean of x plus y times the mean of w. The first term, we have the mean of x times w plus y times w. And by linearity of expectation, the second term becomes the quantity, mean of x plus mean of y times the mean of w. Now we use linearity to break the first term into the mean of xw plus the mean of yw, and we distribute for the second term to be minus mean of x times mean of w minus mean of y times mean of w. But now we can just say that the first and the third term is the covariance of x with w, and the second and the fourth term is the covariance of y with w. Second property is scaling. If we look at the covariance of a times x with y, that's the mean of the quantity a and x and y minus the mean of ax times the mean of y. In both instances, the a can be factored out, and factoring the a out of the two terms leaves a times the covariance of x and y. The third property is commutativity, which is even easier. The covariance of x and y is the mean of x times y minus the mean of x times the mean of y. Multiplication inside the expectation is commutative, and the multiplication of the means of x and y is commutative, and so we're left with the covariance of y and x. The last property, a little trickier, says that if an inner product is non-negative, but only equals 0 when the vector is 0. Now, in order to show this final property, we're going to need to define our vectors a little bit more carefully. I'm going to say that a random variable x is shift equivalent to y if there exists a constant c such that x plus c and y have the same distribution. So for instance, if I have a uniform over 0, 2 and a uniform over 8, 10, those are shift equivalent because I can just add 8 to the first uniform to get the same distribution as the second uniform. So for us, a vector technically consists of a set of shift equivalent integrable random variables. In particular, all constants are shift equivalent to the random variable that is 0 with probability 1. So with that in mind, for all integrable random variables x, it holds that the covariance of x with itself is greater than or equal to 0. Moreover, if the covariance of x with itself equals 0, then there exists a constant c such that the probability that x equals that constant equals 1. Here's the proof. The square of any number is non-negative. So the covariance of x with itself is the expected value of the square of the centered random variable. That random variable, being a square, is greater than or equal to 0, and so the mean is greater than or equal to 0. So now let's go the other direction. Let's assume that the covariance of x with itself equals 0. And let's let epsilon be any number greater than 0. Then indicator functions are always 0 or 1. So if I multiply a non-negative expression by an indicator function, that can only possibly make it smaller. So 0 is the mean of the centered random variable of x squared. That is greater than or equal to the mean of that centered random variable squared times the indicator of this expression. The difference between x and its mean in absolute value is greater than or equal to epsilon. Now for the indicator to be 1, it's true that the centered random variable x is greater than epsilon squared. So I can use another greater than or equal to sign and replace this square of this centered random variable by epsilon squared. But epsilon is just a constant. So I can factor it outside of the expectation, leaving the expected value of the indicator of something. That gives me the probability that the thing inside the indicator occurs. Now, both of these are non-negative. Probabilities are non-negative. Epsilon squared is non-negative. So that's greater than or equal to 0. But we also know that it's less than or equal to 0. Only way that can happen is if it's 0. Epsilon squared was greater than 0. So that tells me that the probability that x is different from its mean by more than epsilon is 0 for all epsilon greater than 0. In particular, that's true for epsilon equal to 1, 1/2, 1/3, 1/4, and so on. And that gives us a countable sequence of events whose total probability is 0. The negation of the union of those events then gives the probability that the difference between x and its mean is 0, it has to be 1 minus 0 or 1, which completes our proof. Taking all four of those facts in consideration, covariance is an inner product. That's going to come in handy next time when we use more facts from linear algebra about inner products in order to learn more about how the covariance behaves. So that's how it works. By treating our random variables as vectors, we have this notion of an inner product, which we call the covariance, which measures how closely two random variables are related. See you next time.